Welcome viewers to the third lecture for the online series of lectures for the course of General Relativity. Towards the end of last lecture, we discussed how the components of a tangent vector transforms under change of chart. This lecture will start discussing covectors. So we start our discussion by covectors. This section can be considered as linear algebra revisited. Okay, so here's the definition. Let V be a real vector space. By real vector space, we mean that the ground field is the set of real numbers, real vector space. The dual vector space V star, which we denote by V star of V, is a vector space consisting of linear maps from V to R. So we consider all linear maps from V to R, and the collection of all these transformations constitute the dual vector space V star. Okay. All right. If V is a finite dimensional vector space whose dimension is n, in other words, if V is n dimensional, then so is V star. Okay. So here we are writing a set consisting of these vectors where mu runs from 1 to n. Then, since V is a finite dimensional vector space, we denote the set of basis elements of V by this set. Okay, this is basis of V. This is a set consisting of n linearly independent vectors of V that span the vector space V. Okay. Similarly, we have another set of n vectors from V star, which are all linearly independent and span the vector space V star. These are precisely the basis elements of V star. So here is the basis of V star, mu running from 1 to n. Note that the index here is a subscript for the basis elements of V, and the index is superscript for the basis elements of V star. Okay, and a basis element of V star acts on a basis element of V in the following way. F mu acting on E nu is the Kronecker delta mu nu. Okay. So using this relation, we immediately see how a generic vector in this vector space V can be acted upon by a basis vector of V star. In other words, if F equal to X mu E mu is a generic element of V, see that here summation is implied. We are following Einstein's summation convention, meaning that this expression is precisely x mu e mu when the sum is taken over all mu's from 1 to n. Okay, it means that in this linear combination, the coefficients are x mu's, which are just functions, and e mu's are the basis vectors of the vector space V. Okay, now if we take a basis element of V star and act it upon a vector from V, a generic vector from V, we then expand X as a linear combination of the basis vectors. Okay. F mu and x mu e mu, and x mu can be taken out, just a pure function, and the action of f mu onto e mu is given by delta. Well, I don't want to skip any step. This is f mu e mu, then you have x mu delta mu nu, and you just left with x mu. Okay, so we get f mu acting on this generic vector of the vector space V to be simply x to be mu, x mu, meaning that which is the muth component of the underlying vector x of the vector space V. Okay, good. Now we see that since V and V star have the same dimension, okay, they are isomorphic vector spaces. This is a very basic stuff from linear algebra. Two vector spaces of two finite dimensional vector spaces of same dimension must be isomorphic to each other. Okay, have the same dimension, they are isomorphic. They are isomorphic vector spaces. Okay. And this is how we denote this isomorphism. Is the desired isomorphism. Okay. Well, this isomorphism is actually basis dependent. There is a more natural isomorphism between, contrary to this isomorphism, there is a more natural isomorphism between V and V star star. The dual of the dual vector space. Okay, what is that? Well, in order to, we have a theorem here, I just state it without proving it. Okay, if V is finite dimensional, if V is finite dimensional, then V star star is naturally isomorphic to V, is naturally isomorphic to V. Okay, and this isomorphism is given by, and this isomorphism is given by this map phi from V to V star star. Okay. With phi of big X, okay, big X, well, big X is an element of V, okay, it's a vector, it's a generic vector of the vector space V, okay. So phi X is expected to be in V star star, okay. So this guy is an element in this space, V star star, okay. Okay, so it is supposed to act on an element in V star, okay. So I choose an element omega in V star, okay. So it acts on omega, which is an element of V star. So what is the result? So an element of V star star is expected to act on an element of V star to give a real number. Okay. Well, that's how we define the dual. All right. So it is expected to be a real number, and this real number is defined by this expression, because we already know that omega is in V star, and since X is in V, then omega acting on X is supposed to give you a real number. And that real number is precisely this real number. Okay, good. Now we get back to our discussion on manifold. Get back to our discussion on manifold. Here is a definition. So remember that we had the structure of manifold, and at each point of the manifold there is a tangent space, right, which consists of all the tangent vectors going through that particular point in the manifold, like this. The collection of all these vectors constitute a vector space called the tangent space at that point of the manifold, right? That we denoted by TPM. M is a differentiable manifold, P is a point on that differentiable manifold, and TPM stands for the tangent space at that particular point on the manifold. It has a vector space structure that we studied earlier. An element in this, or a tangent vector in this vector space, is denoted by X restricted to P. Okay, so it makes sense to talk about, the addition of two tangent vectors in this vector space and multiplying a real number alpha with this tangent vector to give a new tangent vector from the concept of vector space. Okay. Now the dual space of TPM, denoted by TP star M, is called the cotangent space of M at P in M. Okay, so we gathered the generic notion of a dual vector space earlier. Now since TPM is a vector space, we consider its dual vector space, that is TP star M, which is called the cotangent space of M at P in M. Okay, good. So a tangent vector, so an element of TPM is called a vector or a tangent vector, and an element of Tp star m is called a covector. Covector. Okay. So there is a caution here. This is not 1,4 as discussed in the lecture notes by Rio. So the dual notion of a tangent vector is a covector, not 1,4. Okay, we'll come to the concept of one form later in this lecture. Okay, so this is an element of Tpn, which is a vector, and suppose omega restricted to P is an element of Tp star m, which we call a covector. Okay. Now we come to the definition of vector field and 1,4. Vector field and 1,4. Okay, so here is the definition of a vector field on a differentiable manifold. A vector field X on a differentiable manifold M is a map X from C infinity M comma R to C infinity M comma R. Okay, this is the vector space of all functions from M to R. Okay, or you can call it the space of real valued functions on M. Okay, it has a vector space structure. Okay, it is endowed with other structures as well that we will not discuss now. It has something called it's a vector space. It is not a finite dimensional vector space, but let's not discuss those details here. It's a vector space. It consists of all functions from M to R. In other words, it consists of all real valued functions on M. That's good enough for the moment. And X is a map from C infinity M comma R to C infinity M comma R, meaning that if you have F from C infinity M comma R, a function, then X, the vector field acting on F, is again a C infinity function on real valued C infinity function on M. Okay, in other words, X is an operator. We know that operator is something that takes a function to another function. Okay, so let F is an element of the vector space C infinity M comma R. Then XF is, we can write it as X mu del by del X mu. Okay, acting on F. Okay, so this is how I am rewriting X. Okay, and mu goes from 1 to n. So this expression is summed over all mu's running from 1 to n, where X mu's are smooth functions on the manifold. Okay. So this is how you view this expression. It's a multiplication of two smooth functions. Okay, del by del x mu acting on f gives a function, and x mu is a function. It's a multiplication. No, pointwise product of two smooth functions. Okay. So now observe the following. Now we want to explore the relationship between a tangent vector and the vector field. Okay. So xf is, we have seen that this is the C infinitive function from M to R. In other words, it's a smooth real valued function on M, and this function evaluated at P gives you a number, right? Which is the same according to what we have written down here in the basis del over del x mu in the tangent space TPM. So we can write this as this, right? Okay. So x mu p is a number. So x mu is a smooth function on the manifold, and x mu at p is the function evaluated at that point p, which is just a number. Okay. Similarly, del by del x mu hitting on f is another function, another smooth function, and that function evaluated at p is again a number. So two numbers getting multiplied with each other, resulting in a new real number. Okay. So on the right side, so we're rewriting it as x mu at p and del by del x mu at p acting on f, right? Something like this, right? Which is of course, x at p acting on f, right? So on the left side, we have the vector field x acting on the smooth function f, and that new function xf is evaluated at p, which is a number. Okay. On the right side, I have the tangent vector xp being an element in TPM, and we know from the definition of tangent vector that it acts on a function to give a number, right? And on the right side, we have again a number. These two numbers are meant to be equal to each other. Okay. So this is how the notion of vector field is connected to the notion of tangent vector at a given point on the manifold. Okay. Good. Now the concept of 1,4. The dual notion. So we saw that the dual notion of a tangent vector is a covector, right? So what is the dual notion of a vector field? The dual notion of a vector field is called a 1,4. The dual notion of vector field on a smooth manifold is called 1,4. Okay. So we have seen earlier that we have this vector field x, and we restrict it to a point, meaning that if you restrict a vector field to a certain point on the manifold, that gives you a tangent vector, right? Similarly, if you have a one form and you restrict it to a point of the manifold, that gives you a covector. So this assigns a covector at each point P in M. Okay. So if you have a vector field X, it assigns a tangent vector at each point P. Okay. X is a vector field, assigns a tangent vector X at P in TPM. Okay. So if you have a one form, it assigns a covector omega at P belonging to TP star M. Okay, so we see from here that the dual notion of vector field is one form, whereas the dual notion of a tangent vector is a covector. Okay, and a vector field assigns a tangent vector at a given point on the manifold, and a one form assigns the covector at a given point P on the manifold. Okay, now given a smooth function, say we are given a smooth function, a real valued smooth function, so writing it in bracket, real valued. By real valued I mean that f is a function from M to R. Okay, on M. So in the literature it's called a germ, which is a local concept of a function on the manifold. Okay, one can write down a one form. So given a smooth function, smooth real valued function on M, one can write down a one form df such that it assigns at each point P in M a covector, right, which is an element of the cotangent space at the point P of M. And this is an element of the dual space of the vector space TPM, right? And this is given by, because an element of the dual space acts on a vector of the underlying vector space to give a number. So if this guy acts on an element xp of TPM, so we see that df at P is an element of the cotangent space, and x at P is an element of the vector space TPM. So it is supposed to be a number, and we define this number to be equal to x f, right? Remember, x f is a function, and that function is evaluated at P, which is going to be a number. This is the same as x at P acting on f. The tangent vector acting on a function gives you a number. So this guy belongs to TP star M, this guy belongs to TPM, and this is just a number. Okay, This is how we define the action of an element of TP star M onto an element of TPM, resulting in a number. Good. Note that we denote a vector field and one form so I want to be more precise about it, exact one form in our case, but there are more general one forms. But for the moment, let's forget about the specifications. We'll deal with these things in detail in differential geometry. But for the moment, let's say that we are dealing with exact forms. So we denote a vector field and one form, which is of course in this case an exact form, by x and df respectively. Okay, and a vector and co-vector by x at p and the corresponding co-vector as df at p. Okay, so this guy is a vector field, this guy is a one form, this guy is a tangent vector or just a vector, and this is the co-vector. Okay, respectively. Okay, so recall the definition of a one form, or no, it's not actually one form that we are discussing. It's the action of the co-vector on a tangent vector, and that we have already seen. df at p acting on x at p is given by x f, this function evaluated at the point p. This is how we define this action. Now let x1, x2 all the way up to xn be a chart defined in the neighborhood of P. Defined in the neighborhood of P. Okay, so then the basis of TPM, since TPM is a vector space, then the basis of TPM reads del by del x1 at P, del by del x2 at P, all the way up to del by del xn at P. There are n basis elements. Why? Because TPM is an n-dimensional vector space. Okay, the tangent space at the point P of M. And while, so we are not moving into the, going into deep into the details of these aspects of differential geometry, but we need to know the facts. Okay, while the basis of TP star M, the corresponding cotangent space at P, the dual space of TPM, basis of TP star M is dx1 at P, dx2 at p all the way up to dxn at p. Okay, so now these are the basis elements of TPM, right? And these are the basis elements of TP star M. Okay, so there is naturally an action of these elements on these elements, okay, and which is given by, if I choose dx mu at p acting on del by del x mu at p, right? So this is what we already defined here, right? So using this definition, we see that this is nothing but del by del x mu at p. Well, same as x at p acting on f. This is x mu, right? And this is nothing but by the definition partial derivative. Okay. Good. We need some space now. The covectors. So here we took a basis element of TP star M. Instead of taking a basis element of TP star M, if we choose an exact form and which assigns a covector at a given point, the covector, if we choose this covector associated with the exact one form df, this guy acts on the basis vectors of TPM in the following way. df at p acting on del by del x mu at p. Okay, and this is nothing but what we have discussed. From what we have discussed so far, it's going to be del f by del x mu at p, which is the number, right? Okay, and we know that we have called it earlier like this, right? And this was defined. So we defined the partial derivative at a given point on the manifold as, remember, del by del x mu at phi of p f whole with phi inverse. Okay, this is how we define this guy or this guy, they are equivalent. Okay, from which we conclude the following. So which means that, so on the left side, what do we have on the left side? On the left side, this is a covector. A covector is an element of vector space Tp star n, which is dual to the vector space Tpn. We have already learned that. So now, since it's a vector in this vector space, it has a basis expansion. Let's do the basis expansion of this guy in Tp star n, which reads as follows. We are writing this, numbers as this. Okay. There may be different notations, but we stick to this notation. So if I choose a vector, df, vector or covector. So covector is a kind of vector as well. So this guy is an element of this vector space. In that sense, I'm calling it a vector, but it's in the dual vector space. That's why you call it a covector. So you expand it in terms of basis elements of Tp star n in this way. So these are the, so we are denoting these things inside the square bracket as the coefficients, and these are the basis elements. These are the basis elements. So this is the basis expansion of this generic covector in Tp star. So now we are going to write it as this. This is only df at p. Okay. And this guy acts on this basis element of Tpm, right? And on the right side is this expression, del by del x mu, evaluated at phi of p of this expression. Okay. So now it implies that, so this is just a number. So it doesn't do anything here. It acts on this guy. This guy acts on this expression, on this covector, basis covector acts on this basis tangent vector to give a Kronecker delta, right? df at p mu, and there is this Kronecker delta mu is equal to del by del x mu of this expression f composed with phi inverse evaluated at the point phi of p. So which means that the mu component of this covector df at p is going to be equal to del by del x mu at phi of p f composed with phi inverse. Okay, good. So if I choose the covector corresponding to an exact 1,4 lying in Tp star n, then, and I basis expand it in this way, right? The newest component of this covector is this guy, and these are the basis elements. Then these coefficients are given by this expression. Okay. Now let me ask the following question. How do the covector basis elements dx mu at p and covector components So remember that when we were earlier we were talking about the exact one form, okay, which we denoted by df, okay, and the corresponding covectors were df at p. Now we take more general one forms which we denote by omega, okay, which this is the most general one form that one can have. Omega is a one form, and omega at p is a covector. Okay, so it's a covector, and you write this covector, you basically expand this covector to write it as omega mu at p, which is of course a number, and this is the basis. These are the basis elements. So this is how we basis expand the covector corresponding to this one form omega. Okay. Now we are not dealing with exact one forms, we're dealing with the most general one form. So omega is the most general one form, and omega at p is going to the corresponding covector, and this is the basis expansion of the covector in terms of the basis elements of tp star. Okay, so now we are raising the following question: how do the covector basis elements tx mu p and the covector components omega mu at p, these numbers, okay, for a given covector, in tp star m transform under change of basis or change of charts. Meaning that if we go from one chart to another chart, how do these things change? The basis covectors and the covector components. Okay, we need to say this. Okay, we'll have a look at it in the next segment. Thank you for attending the first segment of the third lecture.